Okay. Finally today, let's take a look at aliasing in sinusoids, because it's a topic we can treat mathematically, and look into this phenomenon of aliasing a little bit more. Turns out, this is easy to show, that if I'm sampling any sinusoid with a frequency f0, if I also sample any sinusoid that has a frequency mfs above f0, where m can be any integer, when I sample this, I'm going to get samples at nt, and then I can rewrite this as 2 pi f0 nt, and then plus I'll have the 2 pi factor m n times 2 pi, where I'm using the fact that f of s times 1 over t is f of s times t is equal to 1, or f of s is equal to 1 over t. And so that fs t product just becomes 1. Well, now m and n are integers, so this is just a phase shift of an integer multiple of 2 pi. So sampling this higher frequency signal, where this signal has a frequency of f0 plus mfs, those samples are indistinguishable from samples of the sinusoid with a frequency of f0. Again, it seems a little hard to believe perhaps, but let's look at a specific example where let's talk about, I want to sample a sinusoid that has a frequency of 400 hertz, and I'm going to sample at 1000 hertz. Okay, so the corresponding sample time would be the reciprocal of that, or 1 millisecond. And then now of course here I'm meeting the Nyquist criteria. I'm sampling at more than twice 400. But now let's look at what happens if we sample a sinusoid with a higher frequency. In particular, I'm going to let m equal 1 here, and then so fs is 1000, and then look at sampling this higher frequency signal now at the same sampling rate. Of course, I'm violating the Nyquist criteria here, and this is what's causing this problem. I'll just actually make a table for different values of n, and then my sample instances are nt, and then we can evaluate sample values of x, and then also y. So 0, 1, 2, 3, 4, and then the sample instances, this would be 0 milliseconds, 1 millisecond, 2 milliseconds, 3 milliseconds, and 4 milliseconds. So if I plug in t equals 0 here, of course for both of these I'll get 1, because cosine of 0 is 1. But if I plug in 1 millisecond into this expression for x of t and evaluate that on my calculator, I get minus 0.809. Okay. Maybe a little bit surprising, and I asked you, you should verify this. If you plug in 1 millisecond in for y of t, I get exactly the same value. And the same is true for the other sample values at 2 milliseconds. Both of them give me sample values of 0.309. That appears again actually at 3 milliseconds. And then at 4 milliseconds, I get negative 0.809. And so, looking at just the sample values after sampling x of t and y of t, the sample values are identical. I can't tell that whether I've sampled this continuous time signal that originally had a frequency of 1400 hertz, or whether I sampled a continuous time signal that had a 400 hertz frequency. Of course, this would also be true for m equal 2, so 2400, 3400, 4400, 5400, sampling those higher frequency sinusoids, sinusoids whose frequency violates our Nyquist criteria. Those sinusoids in the discrete time domain appear to be lower frequency sinusoids. This 1400 hertz signal is indistinguishable from this 400 hertz signal. So I can't tell, looking at this table, which is all I have, I can't determine what the original frequency was if I'm violating that Nyquist criteria. So in this particular case, y of t appears to have a frequency I'll call Fa equal to 400 hertz. Okay. As a matter of fact, all signals, continuous time signals, will appear to have frequencies that are in the range minus Fs over 2 less than Fa less than Fs over 2. So in the previous example, we were using a sample rate of 1000 hertz. So after sampling, all sinusoids will appear to have frequencies then in the range between minus 500 hertz and 500 hertz. And we can find that what appears to be the frequency in this band. This is called the fundamental band. By finding the largest value of m such that Fa falls within this interval. And again, this can be done for all continuous time sinusoids. Further, we can take this one more step. Since cosine of minus 2 pi f0 t plus theta is equal to cosine of plus 2 pi f0 t minus theta, all frequencies in this negative frequency interval between minus Fs over 2 and 0 will appear to be sinusoids having frequencies between 0 and Fs over 2. This leads to the concept of the apparent frequency of a sinusoid, and that's just equal to the absolute value of the expressions above, and the apparent frequency will always be in the range between 0 and Fs over 2. So all continuous time sinusoids will appear to have frequencies in the range between 0 and this half the sampling rate. In our previous example with a sampling rate of 1000, and all sinusoids will appear to be equivalent to sinusoids that have frequencies between 0 and 500 hertz.